Okay, on this last example, I'm going to show you how to put it into parametrics in your calculator. So we first have to write the equations, and this one is from a height of 5. So we need to write them using an initial height. Again, it's in feet, and the angle is 15. So we'll go x equals initial velocity of 25, and then cosine 15 times t, and y equals negative 16t squared plus 25 sine 15 times t, and then this time we have a plus an initial height. Okay, if there's initial height, you tag that on the end. Now what you can do on your calculator is you can put this into parametrics. So F3 type, if you choose F3 again, you get parametrics. And then you have x and y in each color. So you're going to put in 25 parentheses cosine 15. And when you hit the x, it actually is a t. Okay? So what's going to happen this time is the horizontal distance and the vertical distance are going to be plotted, but no time. We're not going to be able to see time. And so now we put the y in, negative 16 x squared, which is going to make it a t when I hit that button, 25, and then sine 15 times t again, and you just hit the x and it turns into a t, and then you go plus 5. Now before you graph it, you want to look at your window, because we have x and y max, which those are probably not good numbers. I don't need to see many negatives, so I'll make this negative 1. X max is how far it's going to travel horizontally, so it'll probably go a lot more than 10, so I'll start with 100 and see what happens. Y, I need to probably go higher as well. Here's what's important. Keep scrolling down to t. You want to start your t min at 0. It's time. You do not want to go to 360 seconds. You must change this. The most you want to go to is about 6 seconds. And then this pitch, this is really, really, really important. You want to make that 0.1. Okay, if you leave it 3.6, you won't see anything. So this t right here, when you scroll down on window, is super, super, super important. Make sure that you're in degrees. And so let's see what happens. Okay, I went way too high, but it was just an educated guess, so we're going to switch these to much less. 50 would be fine, and 30 would probably be fine. So now I'll look at that again. Still a little bit more than I need. It has an initial height of 5. The angle was so small, that's why it's not going up very much. But it says find the total time on the graph. You may use your calculator if you want. So if you trace this, so you hit F1 trace, you can get pretty close to where it hit. Okay, so my height is 0.06, so that's pretty close. The time was 0.8 seconds, okay? So the total time is really small. And you can change what t is jumping by when we go to that window if you want. I could do this algebraically, and we'll compare that in a minute. Find the total horizontal distance the arrow will travel. Well, I decide I'm close. I'm not perfect, but it's about 19.319 feet horizontally. See, it says time, and then this is the horizontal distance, and this is the vertical distance. And when will the horizontal distance of the arrow be 10 feet from the starting point? And this says to do it algebraically. So I'm going to set my x thing to equal to 10, because that represents my horizontal distance. And so I'm going to go 10 equals 25 cosine 15 times t. So t is 10 over 25 cosine 15. And I'm going to go to my run matrix and just work that out. So fraction 10 over 25 cosine 15. And, ooh, I don't like that number. I'm going to hit F to D to see, and it's about 414 seconds. Now, if I go back to the graph in parametrics, I can see if that answer is reasonable. So I'm going to trace it again. And I'm going to look when the x is close to 10. Now, that's going to be off because this is only jumping by 0.3, but we're going to see when x is close to 10. Okay, 9.6 and 12. So 9.6 is pretty close. 0.4 on here, the better answer is 0.414. I did this one in parametrics.